In this section, we are going to discuss a little more about chord. Particularly, we will discuss how the chords subtend angles at different points. Angle subtended by a chord at a point. If the end points of a chord are joined to a third point, then an angle is formed. Then that angle is called the angle subtended by the chord. For example, chord AB subtends an angle of 40 degree at C. Angle ACB is called the angle subtended by the chord AB at C, which is 40 degree. Let's see another example. Here chord AB subtends three angles. Which is the chord AB? The red line segment in the figure is the chord AB. So the angles subtended are first angle, angle 1 at point D. We can call it as the angle ADB, which is the angle subtended by the chord AB at point D. Second angle, angle 2 at point C, that is angle ACB, which is the angle subtended by the chord AB at point C. Third, angle 3 at the center of the circle O, angle AOB, which is the angle subtended by the chord AB at point O. Now, let us examine the relationship between the size of the chord and the angle subtended by it at the center. It is stated in the form of theorems. Theorem number 1. Equal chords of a circle subtend equal angles at the center. Given a circle with center O, AB and CD are equal chords of the circle, that is AB is equal to CD. We need to prove angle AOB is equal to angle DOC. Now let's see the proof. Consider the triangle AOB and triangle DOC. OA equal to OD. What is the reason? Radii of the same circle. AB equal to CD. It's a given data. Then OB is equal to OC. What is the reason? Radii of the same circle. So we can say the triangle AOB is congruent to the triangle DOC by SSS rule. SSS, that is side, side, side rule. Therefore, angle AOB is equal to angle DOC by CPCT, that is corresponding parts of congruent triangles are equal. Hence proved. Now let's discuss the converse of theorem. Theorem number 2, converse of theorem 1. The statement is, if the angles subtended by the chords of a circle at the center are equal, then the chords are equal. Given a circle with center O, AB and CD are chords that subtend equal angles at the center. That is angle AOB is equal to angle DOC. We need to prove AB is equal to CD. What is the proof? In triangle AOB and triangle DOC, OA equal to OD. What is the reason? Radii of the same circle. Angle AOB equal to angle DOC. It's a given data. Now OB equal to OC, radii of the same circle. Again we can say the triangle AOB is congruent to the triangle DOC by SAS rule, that is side angle side. Therefore by CPCT we can say AB is equal to CD. Hence proved. Let's move on to the next topic, perpendicular from the center to a chord. Let's examine the relationship between the chord of a circle and a perpendicular to it from the center. For that, we need a circle with center O and a chord AB. A line is drawn connecting the center of the circle and the midpoint of a chord. One will find that length of AX is equal to length of BX, or we can say the line bisects the chord. Connecting with this, we have one theorem. That is theorem number 3. The statement is, the perpendicular from the center of a circle to a chord bisects the chord. So the given data, C is a circle with center O, AB is a chord such that OX is perpendicular to AB. We need to prove OX bisect the chord AB, that is AX is equal to BX. Now let's see the proof. Consider the triangle OAX and triangle OBX. We can see that angle OXA is equal to angle OXB. Both are 90 degree. It's a given data. Then we can see OA is equal to OB. What is the reason? They are both radii. Now OX is equal to OX. It's a common side. So triangle OAX is congruent to triangle OBX by RHS rule. That is right angle hypotenuse side. Therefore, by CPCT, we can say AX is equal to BX. Hence, proved. Let's see the converse of theorem number 3. That is theorem number 4. The statement is, the line drawn through the center of a circle to bisect a chord is always perpendicular to the chord. So, what is given? A circle with center at O. AB is a chord of a circle and OX bisects AB. That is, AX is equal to BX. Right? Now, we need to prove OX is perpendicular to AB. Let's see the proof. Consider triangle AOX and triangle BOX. There we can see OA equal to OB. They are both radii. Now OX is equal to OX. It's a common side. AX equal to BS. It's already given. And so the triangle AOX is congruent to the triangle BOX by SSS rule. What is SSS rule? Side, side, side rule. Therefore, by CPCT, we can say angle AXO is equal to angle BXO. Mark it as equation number 1. Now, take the line AB. We can say angle AXO and angle BXO form a linear pair. That is, sum of angle AXO and angle BXO forms 180 degree. So, angle AXO plus angle AXO is equal to 180 degree. That is from equation number 1. So, 2 angle AXO is equal to 180 degree, or angle AXO is equal to 180 by 2, which is equal to 90 degree. Therefore, angle AXO is equal to angle PXO is equal to 90 degree. That means what we can imply from this, OX is perpendicular to AB. Hence, proved. Next, we will discuss equal chords and their distances from the center. Here we are going to discuss the relationship between the length of the chords and their distances from the center. In the given figure, we have to find the distance of point P from line AB. You can see we can draw multiple lines from point P to line AB, such as PC, PD, PE, PF, PG, PA, PB. All these lines are of different length. So, we consider the length of the perpendicular PE from a point P to a line AB as the distance of the line from the point. Also notice that the length of the perpendicular PE from point P to a line AB is the least distance. That is, length of PE is the smallest of PA, PB, PC, PD, PE, PF, PG, right? So, if point P lies on line AB, then the distance of the line from the point is 0. Now, we will see how length of the chord and distance from center are related. A circle can have infinitely many chords. In the figure given, we observe that the longer chord is nearer to the center than the smaller chord. So, diameter is the longest chord from the center, right? Since the center lies on it, and what about the distance? Its distance is 0. So, AB is the longest chord in the figure shown, and if you refer, you can see IJ is the shortest chord. Also observe that the distance of AB is shortest from center, and while the distance of IJ is the largest, right? Now let's move on to the next theorem, theorem number 5. So let's see the statement. Equal chords of a circle or of congruent circles are equidistant from the center or centers. Given, what is given? A circle with center at O. Now, AB and CD are two equal chords of a circle. So, we can write AB is equal to CD. Now OX and OY are perpendiculars to AB and CD. So we need to prove OX is equal to OY. Let's see the proof. Since OX is perpendicular to AB, perpendicular from the center to the chord bisects the chord. So AX is equal to BX is equal to half of AB. Mark it as equation number 1. Since OY is perpendicular to CD, again we can say the perpendicular from the center to the chord bisects the chord. We get the second equation, that is CY is equal to DY is equal to half of CD. Now given that AB is equal to CD is already given data. Now AB by 2 is equal to CD by 2. So now from equation number 1 and equation number 2, we can say AX is equal to CY, and that mark it as equation number 3. Now consider the triangle AOX and triangle COY. We can say angle OXA is equal to angle OYC because they are both 90 degree. It's already given data. Now take OA. OA is equal to OC. We can say they are both radius, right? Now AX is equal to CY from equation number 3. So we can say triangle AOX is congruent to triangle COY by RHS rule. What is RHS rule? Right angle hypotenuse side. Therefore, by CPCT we can say OX is equal to OY. Hence proved. Let's see the next theorem. Theorem number 6. Chords equidistant from the center of a circle are equal in length. Given a circle with center O, AB and CD are two chords of a circle, where OX is the distance of the chord AB from center. That is, OX is perpendicular to AB. Now OY is the distance of chord AB from center, and OY is perpendicular to CD. Also, OX is equal to OY. We need to prove AB is equal to CD. Let's see the proof. Consider triangle AOX and triangle DOY. Angle OXA is equal to angle OYD. Reason, both are 90 degree, it's a given data. Now we know OA equal to OD, they are both radii. OX is equal to OY, it's a given data. Therefore, triangle AOX is congruent to triangle DOY by RHS rule, that is right angle hypotenuse side. By CPCT, we can say AX is equal to CY and mark it as equation number 1. For chord AB, OX is perpendicular to AB, and we know the perpendicular from the center to the chord bisects the chord. So X bisects AB, that is AB is equal to 2 times X. Mark it as equation number 2. Now for chord CD, OY is perpendicular to CD, perpendicular from the center to the chord bisects the chord. So Y bisects CD, that is CD is equal to 2 times DY. Mark it as equation number 3. Now from equation 1, we can write it as AX is equal to CY, that is 2AX is equal to 2CY, or AB is equal to CD. How? From equation number 2 and 3. Hence proved. So let's have a recap of what we have learned. So far we have learned theorems related to chords. We have seen theorems and its converse related to angle subtended by a chord. And we have the theorem equal chords of a circle subtend equal angles at the center. And its converse, if the angles subtended by the chords of a circle at the center are equal, then the chords are equal. Next, we have seen the perpendicular from the center to a chord, and the theorem, the perpendicular from the center of a circle to a chord bisects the chord, and its converse, the line drawn through the center of a circle to bisect a chord is always perpendicular to the chord. Next, we have seen equal chords and their distances from the center. Connected with this, the theorem is equal chords of a circle are equidistant from the center, and its converse statement is chords equidistant from the center of a circle are equal in length.